Alright, so we're going to continue with our study of galaxies, and the two main things that we want to learn about today are how do we find distances to other galaxies and other objects in the sky, and then how did this lead to Hubble coming up with his famous Hubble law, and what is the significance of Hubble's law. So when we look at this picture, what it's illustrating is that there are objects that are large, that vary in their distance away from us. We have things that are relatively close to us within our solar system. We have nearby stars, we have things in the Milky Way, then we have galaxies that are relatively close to us, and finally galaxies that are very far away from us. And in this picture, what they're showing you are the different methods that can be used to find the distances to these objects. What you want to see here first is the idea that when we want to measure distances, we need to use different methods depending on what we're trying to look at, because different methods are well suited to particular distance or ranges of distances. And the main idea that we're using when we are measuring distances to objects is the relationship between the brightness of an object, its luminosity, and its distance. So the brightness is basically how bright an object appears to us, just its general appearance. Now, luminosity is a term that is new to you because we didn't study stars. We can only do so much, but the luminosity is basically what I like to refer to as the intrinsic brightness. It's truly how much light is being released from that object. What happens is the difference between brightness and luminosity is brightness is affected by how far away we are, because even if an object is releasing a great deal of light from its surface, if we're very far away from it, it won't look as bright because in a sense that light is being spread out over a larger and larger area, and so it becomes less intense. So brightness is something for an object that can change depending on how far away we are from it. But its luminosity is an intrinsic property of an object because it's really truly how much light is that object release. So when we look at stars, we might say, okay, this star right here is much brighter than this one. But you can't say that necessarily that star that is brighter is more luminous, because it could actually be less luminous but is just much closer to us. And so this is a relationship between these three terms that we're going to be exploring and basically exploiting to find distances to objects. So this picture is trying to illustrate to us why brightness decreases as distance increases. So we have a star in the center, and keep in mind the star is releasing light in all directions in a spherical direction because that's the shape of it. And as that light goes out, it actually has to be spread out over larger and larger spheres. So the light coming from this star, when we get to a distance of 1 astronomical unit, is being spread out over this entire sphere here. But as we go to 2 astronomical units, it's being spread out over an even larger area. Because what happens is we're interested in what is the area that the light is being spread out over, and that's the area of a sphere, which is 4 pi times the radius squared. Of course, the radius of our sphere here is also the distance from the object. If we divide the luminosity of the star by the area that the light is being spread out over, we will get its brightness. So this is the relationship between the brightness and the luminosity. The brightness is equal to the luminosity divided by the area of the sphere, or what is more likely, or what we can just remember, is the brightness is proportional to the luminosity, but inversely proportional to the distance squared. So what happens here is, if we know two of these terms here, like if we know the brightness of the star, but we also know its luminosity, we could just rearrange this expression and find the distance. And that's why this relationship is so important, because that's what we're actually trying to find. We're trying to find the distance to nearby objects. If we know the luminosity of the object and its brightness, we can easily find its distance. So for the relatively close objects, a technique that we use to find distance is to measure the stellar parallax. You might remember this picture because we talked about stellar parallax with reference to how our solar system was arranged. Was the sun at the center or was the earth at the center? And we learned that what early scientists realized, if the earth was rotating around the sun, we should observe an apparent shift in the position of a nearby star relative to the background of stars. So we should see, as we go from July to January, we should see the star move from this position in the sky to over here. So notice how the background is exactly the same, but the position of the nearby star has switched. The angle, well, basically actually half of this angle of the shift is called the parallax angle. And it turns out that if we can measure the parallax angle or the shift of a star's position over the course of 6 months, that angle, if it's measured in arc seconds, because remember it is a very small angle, is equal to 1 over the distance. The distance is measured in a unit that we're not familiar with, which is called a parsec. A parsec is equal to 3.2 light years. So you notice that we're looking at things that are pretty far away. We're measuring in light years. It turns out that the parallax method for measuring distance is useful out to about a couple hundred light years. So this is our first method of measuring distance, and it's useful for stars that are, pretty close to us, up to 100 or so light years away. And we can use the parallax angle to measure the distance. When we go further, we're going to use what we call standard candles if we want to measure farther distances. A standard candle is when we know something, we know the luminosity of something that we're looking at. We need to have that object that we sort of know. That's what its luminosity is, and then we can sort of use it to infer the brightness and luminosity of other objects and then find the distance. The standard candle is that object whose luminosity we know, and we don't need to measure its distance to it in order to find its luminosity. So this becomes sort of like our measuring stick, if you will, that we can actually use to infer different brightnesses and luminosities of other objects in the same neighborhood that then can lead us to finding distance. What we're going to find is that in different situations, basically for different distances, we have different standard candles that we use. And so we have to always think about, in a situation, depending on what we want to find the distance to, what would be a good standard candle. So as you see here, once we move off of parallax, we're talking about main sequence fitting, and we'll talk about how that works and what our standard candles are there. Cepheid variable stars become our standard candles as we move into nearby galaxies. And then what will we find? What will we use as standard candles for distant galaxies? So the first sort of standard candle we use is related to this diagram. Again, unfortunately, because we don't have time to do the whole book, we haven't seen this before. This is an HR diagram, which is a way to classify stars. The horizontal axis is the temperature of the stars, and the vertical axis is the luminosity. Down the middle of the diagram, you see a pretty straight line, and this is what we call the main sequence. This is sort of the area where most stars are classified along the main sequence. And if they're on the main sequence, you can see that knowing their temperature and their appearance, we actually will be able to read off directly their luminosity. So we're going to sort of exploit this idea of this main sequence. Basically, what we're looking at when we do main sequence fitting is, first of all, we use a star cluster that's close enough that we can find the distance using parallax. Remember that we found that stars form in clusters, so that's not going to be very difficult. So we have a cluster of stars. We can find the distance using parallax if they're close enough, and then we can use the relationship between brightness, luminosity, and distance to actually find the distance to that star cluster. Once we know that, and we'll know the luminosities of all of the stars in the star cluster, and so we can sort of put it on this HR diagram. Then we find another star cluster that's too far away to use parallax. But what we do is we compare the apparent brightness of that star cluster to the one that we already know about. So the cluster that we already measured the distance is the one that becomes our standard candle. If we compare the brightness of the two clusters, we can actually figure out how their different distances are related. This makes a little more sense when we have a concrete example, so let's take a look. Let's say that we already looked at the Hyades cluster, and we found out how the luminosity of the Hyades, and we know the distance to the Hyades. Then we use another cluster that we want to figure out the distance to, and that would be the Pleiades. Well, if we compare the brightness of the two clusters, the apparent brightness, we notice that the Pleiades are not as bright as the Hyades. So using the relationship between brightness and distance, we could say, well, the Pleiades must be further away. If we measure how much further away they are, if we measure how much brighter one cluster is than the other, for instance here, we say the Hyades is 7.5 times brighter than the Pleiades, which means then the Pleiades are the square root of that times as far away. So the Pleiades we know are further away because they're not as bright, and we take the square root of that multiple because the distance is squared in the relationship. So to find distance alone, we just take the square root. So the square root of 7.5 is 2.75, so we know the Pleiades are almost 3 times further away than the Hyades. Since we've already figured out how far away the Hyades are, now we have a way to be able to say how far away the Pleiades are. I'm going to stop here because we don't want the videos to be too long, and so in the next video we will go over how we can use Cepheid variable stars as a different type of standard candle.